Have you ever found yourself contemplating the scientific credibility of planetary orbits depicted in Netflix's series Three-Body Problem? This intriguing narrative artfully unfolds within the confines of an enigmatic alien civilization, a civilization that has made its home within the tumultuous boundaries of a triple-star system. This system, marked by erratic and wildly capricious orbits, is an integral facet of the show's captivating storyline. The fascinating notion, central to the plot, finds its origins in a complex astronomical concept known as the three-body problem. This problem of celestial mechanics, of predicting the motion of three gravitationally interacting bodies, was first identified and explored by the illustrious scientist Sir Isaac Newton. Newton's work in this field constituted some of the most challenging problems of his era and continues to confound scientists today. The three-body problem presents a conundrum, predicting the motion of three celestial bodies influenced by their mutual gravitational pull. This task is exponentially more complex than predicting the motion of just two bodies. The latter, known as a two-body problem, can be solved with relative ease, while the former retains a level of complexity that remains unsolved in a general sense. Yet, the true enigma lies in how the show interprets and presents this scientific phenomena. The three-body problem is a challenging concept to grasp and an even more complicated one to visually represent. The series, however, manages to weave it seamlessly into the narrative, striking a balance between scientific accuracy and creative storytelling. But the question that lingers is, how much of this captivating and complex concept depicted in Three-Body Problem is grounded in established scientific knowledge? Are the planetary orbits we see on the screen a reflection of the actual celestial mechanics, or are they a part of the creative liberties taken by the creators? Truth be told, there's no general analytical solution for the three-body problem. This topic has been among the most confounding puzzles in the realm of physics and astronomy for centuries. From the time of Newton, who initially attempted to formulate a universal equation to predict the movement of celestial bodies, to the present day, the complexity of this problem has proven unyielding. The three-body problem, as it is colloquially known, involves the prediction of the individual paths of three separate bodies interacting under the influence of gravitational pull. The essence of this problem lies in the challenge it poses to predict the precise orbits of three sizable objects over lengthy time spans. To put it in perspective, it's like trying to predict the exact trajectory of three billiard balls once they've been struck simultaneously, but on an astronomical scale and influenced by gravity. This prediction is monumental, akin to predicting the future in a chaotic and ever-evolving universe. Over the years, the three-body problem has been the focus of numerous studies and research projects, each attempting to decipher the hidden patterns and rules governing such a complex system. It's like trying to untangle a cosmic knot, with each thread representing a celestial body, each affected by the other's gravitational forces. It's a challenging endeavor that requires extensive knowledge in mathematics and physics, a deep understanding of gravitational laws, and a level of precision that is almost beyond human comprehension. Yet, with the arrival of computational techniques, astronomers and physicists can now model such systems with impressive precision, albeit within certain limitations. These modern approaches, backed by powerful algorithms and supercomputers, have allowed us to make substantial strides in understanding and predicting the movements and interactions of celestial bodies in a three-body system. We've not yet fully solved the problem, but we're making significant progress. The depiction of chaotic orbits and unpredictable climate changes in Three-Body Problem reflects the characteristics of chaotic dynamical systems. These systems, a fascinating concept central to the scientific and mathematical fields, exhibit a unique sensitivity to initial conditions. This attribute, often referred to as the butterfly effect, encapsulates the essence of chaotic systems. Even the smallest of changes in the early stages can have a profound impact on the entire system. Take, for instance, the unpredictability of weather patterns, a classic example of a chaotic system. Weather prediction is a complex task that relies heavily on accurate data and precise models. However, the inherent unpredictability and sensitivity to initial conditions make long-term forecasts extremely challenging, if not impossible. The smallest variation in temperature or humidity at any given point can drastically alter the weather conditions in the following days or weeks. This is why meteorologists can predict the weather accurately for a few days, but long-term forecasts are often inaccurate. Similarly, the tumultuous nature of the stock market mimics the characteristics of chaotic systems. Economists and financial analysts, despite having comprehensive data and sophisticated models, struggle to predict the behavior of the stock market accurately. This is because the market is deeply sensitive to a plethora of initial conditions, such as investor sentiment, governmental policies, and global events. So, examples of chaotic systems manifest this sensitivity in a dramatic fashion. Short-term predictions are feasible, but as the timeline extends, the predictability deteriorates. The three-body problem exemplifies these real-world systems in its depiction of chaotic orbits and climate changes, showcasing sensitivity and unpredictability. This makes short-term predictions possible, but as we look further into the future, the predictability crumbles, mirroring the inherent uncertainty of chaotic dynamical. A fundamental aspect of the series' depiction revolves around the captivating contrast between deterministic and stochastic systems. Deterministic chaos, a term that may sound paradoxical to the uninitiated, is based on the laws of determinism. It is indeed this facet that forms the backbone of our understanding of the universe and its myriad phenomena. In essence, deterministic systems outline the precise, ordered, and predictable patterns of the world. An illustrative example of such a system, as mentioned in the original script, is the orbital movement of heavenly bodies. Consider the planets in our solar system. Their paths around the planets in our solar system. Their paths around the sun are not random, but rather they follow a specific, predictable pattern. The word chaos in deterministic chaos is quite misleading, as these systems are far from chaotic. They are characterized by order, predictability, and precision, the diametric opposite of randomness. Conversely, stochastic processes randomness. They are akin to a drunkard meandering aimlessly, without any perceivable pattern or predictability. Stochastic systems incorporate a factor of randomness that makes them inherently unpredictable. Their outcomes are not determined by initial conditions, unlike deterministic systems. Instead, their results are influenced by a series of random variables, each having a certain probability distribution. In simple terms, deterministic systems follow a set path, much like a well-rehearsed dance routine, whereas stochastic systems are more akin to improvised jazz. Free, spontaneous, and unpredictable. The interplay and contrast between these two systems form a significant aspect of the series' depiction, giving viewers a fascinating glimpse into the ordered chaos. Even though Three-Body Problem is filled with fanciful elements like a triple-star system with unpredictable orbits, it's grounded in accepted theories of celestial mechanics and chaos theory. The imaginative leaps made by the author and filmmakers are designed to amplify the narrative journey, not to diminish the scientific credibility. In conclusion, the specific triple-star system in Three-Body Problem might stretch our current astronomical knowledge to the edges, yet the overall ideas of chaotic orbits and unpredictable dynamics are firmly grounded in scientific theory. Netflix's interpretation of Three-Body Problem presents an intriguing portrayal of planetary orbits in a complex triple-star system. It masterfully interweaves scientific theory and imaginative storytelling to craft a captivating universe that perpetuates our curiosity and exploration.